Alright, what's up everyone? In this lesson, we're going to be talking about arc length and arc measure. So let's first talk about what an arc is. So you probably have heard the word arc before when you think about basketball or shooting a basketball. We talk about the arc in someone's shot, right? Um, but more formally in this course, we also talk about like marking congruent angles and diagrams, right? You guys know I always tell you differentiate your arc marks, right? So we've seen arcs before, but we're going to kind of formally talk about what they are and kind of how to measure them and how to view them. So an arc is going to be a portion of the circumference of the circle. So think about picking 2 points on the circle, kind of like this GIF is doing here. This GIF is picking points I and J, and it's separating them into two pieces, right? So we're not always going to have nice animations though. So if you take a look at this cartoon or this diagram on the right, we have points B and C, right? So when we're talking about the arc, there are two different arcs we can be talking about, right? The minor arc is the smaller portion of the circle between points B and C. But then we also have the major arc between points B and C. If you go the other way around and travel that really long distance, the major arcs are going to be that bigger portion. So now that we know what an arc is, we're going to talk about two different ways that we talk about their magnitude. So the first unit of measurement is called arc measure. Now, formally, arc measure means the measure of an angle that the arc creates with the center by connecting two radii. So if you take a look at this center diagram here, right now we have arc AB, which is this portion of the circle. And typically, we have major arcs and minor arcs, but if it doesn't specify, we're always looking at the smaller one. So if we want the arc measure, we got to connect a radius to point B, connect a radius to point A, and we just got to figure out, hey, what's the angle measurement between those 2 points, right? That's going to be your arc measure. That also has a formal name, and you guys got to write this down as well. This is more formally called the central angle, right? The central angle is an angle through the center of the circle, and the central angle is always going to be congruent to your arc measure. Now, for a whole circle, what you want to think about is, you have one point A here, and I always like to compare arcs to running. So you start at point A and you run fully around this circle. You can't really connect any radii, but you can kind of think about, hey, if you run around the whole circle, you go a full 360 degrees, right? Now, in this lesson specifically, and in the next few lessons, we're not going to be talking about the whole circle. We're breaking that circle up. So that value of your central angle and your arc measure is usually going to be less than 360, right? Because 360 is going the full circle. So if you take a look at this last diagram here, you can kind of see arc AB, it gives you the arc measure. So if it gave you the arc measure, you know that you can automatically fill that in for your central angle theta and vice versa as well. Now this is some notation. Arc measure, we have that little lowercase m that always stands for measure, but then for arcs we have our two letters and we have a little arc over them, kind of like a little rainbow. So finding arc measure of the circle below here, now in this example, they give us the measure of our central angle. So we know that our central angle is congruent to our arc measure, literally just by the definition. The definition of arc measure says it's the measure of the angle when you connect the two radii to the center, right? So our arc measure here, the measure of AB, arc AB, is 60 degrees. Now, a big thing is associating arc measure with degrees, because we're going to talk about another form of measuring this portion of the circle, and here we're talking about arc length. So if you take a look at the notation, just notice there's no lowercase m here. So there's no m. So if you see two letters with an arc over it, it's talking about the arc length. Now, arc length is again a portion of the circumference, but it's different. It's not talking about angles anymore. Arc lengths are going to be distances. So again, I like to think about running. So let's say you start at this point A here, and you run on a perfectly circular track, and you end up at point B, right? Arc length is measuring the distance between those 2 points on the circle. Now, this GIF does a pretty good job of kind of showing a representation of that, right? It's literally, think about like physically taking scissors and cutting that portion of the circumference out and straightening it so that you can measure that length, right? And arc length is never in degrees. These are going to be units like inches, feet, centimeters, meters, and so on. So we talk about arc length being a fraction of the circumference, and it all depends on our central angle. But let's go back to a full circle moment for a second. If our theta, right, if our angle in the center, our central angle is 360, what that's referring to is us running around the full circle. So I always like to go back to this running example. Let's say we're running, we start at point A, and we go on our circular track all the way around and end up back at point A. You ran the full circumference. So if you want to know the distance that you traveled on the track, that's going to be equal to pi times diameter, right? Because circumference measures that distance along the circle. So if your central angle is 360 degrees, you ran the full circumference. You're good. But in these lessons, we're never going to be talking about a full circle. We're specifically taking portions of that circle and talking about its measurements. So in this middle example here, we're talking about theta being 180 degrees. So go ahead and fill that in on the diagram. Our central angle there would be 180. And thinking about this again, I go back to running all of the time. Let's say we start at point A and we run around our circular track and we end up at point B, and when we connect our radii to the center, we have 180 degrees that is created, right? So the idea here is I'm not running the full track. If you ran the full track, your angle here would be 360, right? So you got to figure out the portion of the circle that you ran. So if we take that 180 degrees and we divide it by 360, we can see we ran 1/2 of the circle, right? So if you want to find the length of arc AB in this case, you got to do 1/2 of whatever your circumference is. And that's going to give you the distance that you traveled. So in this last example, let's call this arc DC. Let's say we started at point D and we ran around our circular track and stopped here at point C. And we created a 90-degree angle. Again, we did not run the full circumference. We did not run half of the circumference, but we got to figure out how much of the circumference did we run, right? So if you take that 90 degrees and you divide it by 360, you'll see that you ran 1/4 of the circle, right? So if you want to find if you want to find the length of arc CD, you got to do 1/4 of whatever your circumference is. So let's dig into a formula. Now, I don't like remembering this formula because, again, you can just conceptually think about it like we were doing on this slide. But if you are a formula person, then so be it. You got to just make sure that you remember what the letters stand for, what the variables stand for. So S is arc length. So if you ever see S, that stands for arc length. Now this theta over 360, right? This comes from the portion of the circumference that we're running, right? And it's important to know that theta is your central angle. And then this, right, we took our portion of our circumference and then we multiplied it by our actual circumference, right? Now this formula on the right here is the same exact thing, except instead of the capital C, we wrote pi times diameter. But that's just because C equals pi d. So you might see it, or you can use it in either form, but they both mean the exact same thing. So we're going to get into a formal example here, and I am not going to use the formula. I'm going to show you that you don't need the formula to do this. So it says find the arc length of AB in circle P with a radius of 8. So we have R equals 8, and we have a central angle of 60 degrees. So our theta is 60, and it says leave your answer in terms of pi. Now remember, what this means is that when you box your answer, you're allowed to put the pi symbol and leave the pi symbol in it. So again, I think of running. So we're starting at point A. We're running our track down to point B. I want to figure out how much I ran. Well, if we ran the full circle, that would be the full circumference, right? So C equals pi d. In this case, our radius is 8, which means that our diameter is going to be 16. So our full circumference is 16 pi, right? So that means that if you started at A and you ran all the way around and ended up back at point A, you would have ran 16 pi centimeters. Now remember, pi is just a number, so if you did 16 pi in your calculator, that would mean, that you ran 50.265 dot 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 centimeters if you ran fully around the circle. But we're not running the full circle, right? This central angle is going to tell us or help us figure out the portion of the circle that we ran. So if we do that 60 over 360, we'll see that we ran 1/6 of the circle. So we don't need the whole circumference. We need 1/6 of the circumference. So 1/6 of 16 pi. And again, we're leaving our answer in terms of pi, so we don't really have to put pi into our calculator at all, but we can simplify this fraction. If we multiply this out, it's going to be 16 pi over 6. So you can do this in your head, but if you have trouble doing it, you can do 16 over 6 in your calculator, and then just hit math fraction, and that gives you 8 pi over 3. Now again, it says leave your answer in terms of pi, so this is totally fine. If it said to round it to the nearest tenth or hundredth, then you would substitute it into your calculator. All right, next example. So we don't have a picture for this one, so you guys already know we're going to have to draw it. So it says a circle is drawn to represent a pizza with a 12-inch diameter, so D equals 12. And the circle is cut into 8 congruent pieces. What is the length of the outer edge of any piece of this pizza? So again, no picture is drawn. Let's draw one. We don't have to be artists here, but we know that the diameter is 12. We also know that the radius is 6. So I usually fill in the radius. It's a little bit easier. Our picture doesn't get as messy. And the circle is cut into 8 congruent pieces. So I'm not going to draw all 8. Typically, when we're dealing with arc lengths and arc measures, we're just dealing with one portion or one slice. So I still got to figure out what this angle is, though. So we're cutting it into 8 congruent pieces, right? So on a smaller scale, 8 congruent pieces would look like this. But I'm not drawing that because that gets crazy messy. But I just got to figure out each of these angles. If all the pieces are congruent, all of those angles are going to be the same as well. So if we do 360 over 8, we get 45. So that means that the measure of our central angle is going to be 45 degrees. And we want the length of the outer edge of this pizza. So if we put points here, we're basically looking for the distance between points A and B right now. So again, I'm going to use my logic. If you want to use your formula, you can. Or you know what, maybe in this example, we will use the formula. So the formula, we have S equals theta over 360 times pi d, right? So our theta is our central angle. So we have 45 over 360 pi, and then our diameter is 12. So now this one says round your answer to the nearest hundredth. So you are not allowed to leave pi in your answer here. So you can go straight to your calculator right now. And if you want to type in a fraction, hit math and go all the way to the right, hit enter. So you'll do 45 over 360 times pi times 12 and hit enter. So we get that our arc length, and we're rounding to the nearest hundredth, which means we want 2 places after the decimal. So we have, I usually write it longer. I'll write 4.7124, and then I will round it. So S equals 4.71 inches. Okay? Now, in this last example that we do, we're going to be using arc length to draw some other conclusions about the circle. So to be honest, you might need the formula for this one. So it says in circle Q, QR equals 10. So QR is going to actually be our radius. So QR is 10. And it says the length of RS is 8 pi. So they're giving us the arc length. They're giving us S here. And it wants us to find the measure. It wants us to find the measure of RQS. So it wants us to find our central angle. It wants us to find theta. So let's use our formula. So we have S equals theta over 360. And then we get pi d, right? So S we have. Our S, our arc length, is 8 pi equals. Our theta is what we're looking for, so that's going to stay as a variable. If you wanted to, you can even put this as x if it confuses you, over 360. And then we have pi, and our radius is 10, so don't get confused by this. You've got to get your diameter. Our diameter is going to be 20. Now, we have pi on both sides of the equation here, so we can just get rid of them right away so that they don't confuse us later on. So now we have 8 equals x over 360 times 20. So there are a couple of different ways that you can do this. I'm going to divide by 20 on both sides first. And if we do that, we're going to get 8 over 20 equals x over 360. And then you can just cross multiply. So you do 360 times 8 for this equals 20 times x. And if we go to our calculator and we do 360 times 8, we get 2880 equals 20x, and then we'd have to divide by 20 again. And we get 144 equals x. Now remember, x is representing our central angle there. So the measure of angle RQS equals 144 degrees, and we are done. So in questions like this, it might give you the arc length and you might have to go backwards. So in this case, just make sure you're making your list of your variables, substituting what you have in, and then solving for your variable. So this question also wants us to find the measure of the angle in radians. So we found already 144 degrees is going to be the value of theta here. Now, to find it in radians is just a different unit of measurement. So similar to how we have inches, centimeters, and feet, degrees and radians are also just a different way of measuring, a different unit. So you guys are going to get this conversion chart on your reference sheets, so no need to really remember this because you can always refer back to it. But to go from radians to degrees, you have to multiply your value by 180 over pi. We have to go from degrees to radians. So what you have to do is you take your degree measurement and you multiply it by pi over 180. So we're going to take 144 and we are multiplying it by pi over 180. And if we do that, we get 144 pi over 180. And all you need to do is simplify that fraction. So in your calculator, do 144 over 180 and then hit math, fraction, and you get 4/5. So 144 degrees in radians is 4 pi over 5, right? So again, you're going to get this conversion chart on your reference sheet for your tests. So you just got to remember, you multiply by pi over 180, you simplify that fraction. Don't forget to put pi back in there as well. So the answer here, 4 pi over 5 radians, is another way of representing that angle. So this is just a summary page. So we have central angles are formed by the two radii and the center of the circle, depending on the arc that we're talking about, right? So if we're talking about arc AC, we can find that arc measure by making those radii and figuring out the measure of this central angle here. We also have arc length, that's a portion of our circumference, and that depends on our central angle. It's how much of the circumference are we going. So we have this formula we can use. You also might see it as theta over 360 times c, which is kind of what we were doing in that first example. And then you guys have this chart of converting between degrees and radians.